Hey there, we're going to go over some notes for dynamics. So up to this point, everything we've seen in terms of forces have been balanced forces, and those objects were either at rest or moving at a constant velocity. And now we're going to move into situations where we have unbalanced forces. And when we have unbalanced forces, what happens is the object will accelerate. So it could be speeding up, slowing down, changing direction. But in all those situations, now the object is accelerating and it has unbalanced forces. So let's look at a quick example. Let's say I have an object and the weight is equal to 70 newtons. And let's say I'm pulling it up with a rope, so I have a tension, and that force is equal to 105 newtons. So now we're going to use that same concept of we make our net force equation. So my net force in the y direction is going to be tension minus the weight. In the past, we've always set that equal to 0 because it was balanced. But looking at this situation, we can see it's not balanced. Okay, so there is a net force now. So now we can plug in our numbers. So your net force in the y direction is going to equal the tension of 105 newtons minus the weight, which is 70 newtons. So your net force in this situation is equal to 35 newtons up. Okay, it's the net force is in the up direction. So let's say we have another object, and this object has a weight of 12 newtons. And then there is a normal force of 12 newtons. So it's sitting on a table. And then let's say there's a force going in this direction, and let's say it is friction, and the friction is equal to 10 newtons. Okay, so let's say I have a book or something, and I push it, and it's sliding across the table. In this situation, my net force equation in the y direction is going to be the normal force minus the weight. And looking at this diagram that we've made, it's balanced vertically. Okay, so we can still set that one equal to 0. Okay, because vertically speaking, we're balanced. But in the x direction, all we have is friction. So for this one, my net force in the x direction is just going to equal 10 newtons to the left. So it's better to put left or right, up or down, than just putting a negative in there. But when we use our calculations, we would put a negative in there. Okay, and we'll see that as we start working through some practice problems. And so we have this new equation. Okay, this new equation is from Newton's second law. Okay, so Newton's second law can be described from this equation here. The acceleration of an object is equal to the net force of the object, or on the object, divided by the mass. Okay, so this is basically Newton's second law. So the things that determine how much an object will accelerate are the net force and the mass. Okay, so the net force is directly proportional to the acceleration. The mass is inversely proportional. Okay, so as you increase mass, that's going to decrease your acceleration. And so let's work through a few examples applying this new Newton's second law. So this question says, in each of the objects below, they have a mass of 5 kilograms and calculate the acceleration of the object. So let's draw object 1, and let's say object 1 has the same as earlier, your Fg is equal to 70 newtons, and then that tension is equal to 105 newtons. Okay, we made our net force equation earlier, and we found that net force, so the net force in the y direction was tension minus weight, and it equaled 35 newtons. Okay, 105 minus 70. So now we're going to go one step further, and we want to find the acceleration of the object. Okay, how much is it accelerating? So Newton's second law says that is the net force divided by the mass. So we plug in our net force, which is 35 newtons, divided by the mass, and it told me that the mass is 5 kilograms. So for this one, my acceleration is equal to 35 divided by 5, which is 7 newtons per kilogram. And let's look at that second one that we drew earlier. We said that it had a weight of 12 newtons. It had the normal force of 12 newtons. And then there was friction going to the left, and that friction was equal to 10 newtons. So in the x direction, that's the direction that we're accelerating, okay, because we're balanced vertically speaking. So we said the net force in the x direction was just equal to the 10 newtons to the left. So then my acceleration for this one is going to be, again, the net force divided by the mass. So that's 10 newtons, or negative 10. Okay, so when you plug in your net force here, I'm going to put negative because it was to the left, divided by the mass, which is 5 kilograms. So you end up with negative 2 newtons per kilogram. Now, sometimes it's usually more convenient, so rather than saying negative 2, you can also say acceleration is equal to 2 newtons per kilogram and state the direction to the left. Okay, so that indicates that negative. So let's look at another one. This one says that we have a 4 kilogram object is pulled to the right by a string that has an 80 Newton force, and it's causing the object to accelerate to the right at 1 meter per second squared. And we want to find the friction on the object. So let's start out, let's make our free body diagram. Okay, so we know we have Fg down. There's going to be a normal force here. They told us there's tension, and then there's some friction. Now I drew the tension, and that's kinetic friction. I drew the tension a little longer because it told me that it is accelerating to the right, so it should be unbalanced on the right side. Once you make your diagram, we can make our equation. So net force equation in the x direction is tension minus friction. Net force in the y direction is the normal force minus the weight. So there's my net force equations, and we're trying to solve for the friction. Okay, so we're going to end up using this equation up here, right? And the equation, we know tension, but we don't know the net force. So we need to find that net force on that object before we can use this net force equation. So remember, Newton's second law says acceleration is equal to our net force divided by the mass. Well, the problem told me the acceleration, okay, so we know this, and they told me the mass. We know this. So we have one unknown. So we can rearrange this equation to solve for the net force on the object. So we're going to multiply both sides by the mass. Okay, so I'll multiply this side by mass, this side by mass, and that cancels. So what we're left with is the net force of the object is just equal to the mass of the object times its acceleration. So let's plug in what they told me. They told me that the mass is 4 kilograms. And they told me the acceleration is 1 meter per second squared. So then my net force is just equal to 4 newtons. Remember, 1 kilogram times meter per second squared is just a newton. So now we know the net force. Put a check there. They told me the tension. I'll put a check there. So we can solve for the friction using that net force equation. So if we Let's rewrite that equation. So we said the net force in the X was equal to tension minus the friction. So I'm going to add friction to both sides. That cancels there, so plus the friction over here. Let's rewrite that. So we have the friction plus the net force is going to equal tension. Now I'm going to subtract the net force from both sides. And it cancels on that side. So what we're left with is the friction in this case is equal to the tension minus the net force. Okay, so the problem gave me the tension. They said tension was equal to 80 newtons. We used Newton's second law to find the net force, which was 4 newtons. So your friction is just going to equal 76 newtons. Okay, so sometimes the object or the problem will give me the acceleration. Sometimes it might give you the net force, but we can still use Newton's second law to solve for those kind of problems, just depending on what they give me. Let's look at one more example. Okay, so this one says we have a 40 kilogram sled. It's drug across a level surface by a rope that has 280 newtons and it's at a 30-degree angle. And then they give me the coefficient of static friction and the coefficient of kinetic friction. So sometimes a problem will give you both and you need to figure out which one you're going to use or if you need to use both. It just depends on the situation. So remember, we'll make our free body diagram. We have tension and now it's at an angle. We know we have Fg. There's also a normal force, okay? So the normal force here needs to be smaller than Fg because I have a y component of the tension there. And then we have this friction here as well. And it's moving, okay? It's being dragged across, so it's going to be kinetic friction. Let's make our net force equations. So in the x direction, we're going to have that Tx minus the kinetic friction. And then in the y direction, we're going to have the normal force plus that Ty minus the weight of the object. Now, vertically speaking, I'm balanced, okay, because they're telling me that I'm accelerating in the right direction. Okay, I'm on a level surface, so I'm not accelerating up and down. So I can set that equal to 0. Now, we also know that the acceleration of the object, because we're trying to determine the acceleration is going to equal the net force divided by the mass. They gave me the mass, okay, so I'll check that off. We have that. So I need to figure out the net force, okay, the net force in the x direction. So to figure out the net force, there's a few things we're going to have to do, okay? We need to figure out friction and Tx. We have to find both of those before we can determine the net force. So let's go ahead and start. Let's start with our tension in the x direction. Okay, so I'm going to kind of blow up this little triangle right here. We have tension going this way, and our tension was equal to 280 newtons. We have our Tx here and our Ty here. So your Tx, and this is 30 degrees, theta is equal to 30 degrees. Your Tx is adjacent to that angle, so we're going to use the cosine function. So we end up with T cosine theta. So we can plug that in. We get 280 newtons times cosine 30 degrees. And when we plug that in, we should end up Tx is equal to 242.5 newtons. So now we know the Tx. The next thing we need to figure out is our friction. And so for the friction, remember the equation for kinetic friction, and it's kinetic because it's moving, is that coefficient of kinetic friction, which they gave me right here, times the normal force. But we don't know the normal force right now. Okay, we know the weight of the object, but we need to know the normal force. Okay, so in order to find the normal force, we have to also find this y component. So back at our triangle, let's solve for the y. Okay, so then we can solve for our normal force. So for our ty, that is going to be opposite the 30-degree angle, so we're going to use a sine function. So we end up with t sine theta. So we can plug that in, and we get 280 newtons times sine 30 degrees. And you end up with Ty is equal to 140 newtons. So I know the Ty and I know the weight, I can solve for the normal force. So let's kind of expand this here. Okay, the normal force plus Ty minus the weight equals 0. So we're going to solve for the normal force. I'm going to add the Fg over, subtract the Ty. So your normal force is equal to Fg minus Ty. Okay, it told me that the sled was 40 kilograms. Be careful, that's mass, right? So Fg equals mg. Your mass is 40 kilograms. And we multiply that by 10 newtons per kilogram. And that equals 400 newtons. So your normal force is equal to 400 newtons minus your Ty, which we found over here, which is 140 newtons. So your normal force then is just going to equal 400 minus 140. You end up with 260 newtons. So we know the normal force now, and they gave me the coefficient. So now we can solve for that, excuse me, we can solve for that kinetic friction. So we'll go back to this. Kinetic friction is equal to the coefficient, and they told me here was 0.5 times our normal force, 260 newtons. So my kinetic friction then is just equal to 130 newtons. So now that we know our kinetic friction and we know Tx, we can solve for the net force using our net force equation. Okay, so the net force in the x direction, up there, we had said it was equal to our Tx minus the kinetic friction. So Tx minus our kinetic friction. So Tx, when we solved, we got 242.5 newtons. Minus when we found our friction, we ended up with 130 newtons. So our acceleration then, I'm sorry, our net force in the x direction is just going to equal 112.5 newtons. So the last step is we can finally apply Newton's second law to find the acceleration of this object. So the acceleration of this object was the net force divided by the mass. Our net force was 112.5 newtons. And then the mass of the object is 40 kilograms. Okay, it's the mass there, not the weight. So we're going to go back and use our 40 instead of 400 newtons. So your acceleration is equal to 2.8 newtons per kilogram. So on these problems, it's always important because sometimes you have to solve for multiple things in order to finally use that equation there. So always start out step 1, make your free body diagram. Step 2, make your net force equations. Step 3, identify what you're solving for. Okay, so I was solving for the acceleration, Then I can determine what all I had to solve for. So for this problem, once I figured out in order to apply Newton's second law, I had to find the net force, which told me I needed to find my x, my Tx, and my kinetic friction. And then in order to find friction, I wrote down my equation and I figured out that I needed to solve for the normal force. Okay, so it's always good to write all these steps out because sometimes you got to solve for multiple things in order to solve for the final answer.